Hello, hello, hello again. Wow, the room is actually looking really nice and full. I see people in the back even. Like this is great. Y'all are really keeping this good, this Supercon. I'm so proud of you all. Thank you. But we have now something admittedly like when I saw the name of this talk, I definitely thought I was in for something a little bit unusual for Supercon programming because we have cats turned plumbers. But then I read the rest of it and realized that embedded Linux makes a little bit more sense within the context of this event. Our next speaker is an electronics engineer who is passionate about technological development and science. He is the co-founder and CTO of Electronic Cats, a company where he develops embedded systems. So, like again, this is in fact a relevant talk, so please don't leave. It is not maybe actually about cats being plumbers. But then again, we might be surprised. Please welcome to the Hackaday Super Conference stage, Eduardo Contreras.
Wow. Hello, everyone. Happy to be here. Thanks for the introduction. I'm really happy again for being able to be present here at the Supercon. I've been working with Hackaday for some years right now, and this is my first time I was able to come here because of the different events. So I'm really happy and thrilled of this. And yes, they mentioned we are going to be talking a little bit of cats, plumbers, and Linux. But me, I'm an electronics engineer. I am a co-founder of Cats. I really love RF, all that stuff that Charles was talking about later. No, before was really crazy for me. It's really I'm a big fan of all radio frequency. I'm a big really fan of craft beer. Also a musician, and I'm a big fan of board games. So if you want to talk about something else than electronics, there you go. About us, Electronic Cats, we are a company founded back in 2017. We do a lot of open source projects that you may know or you may not know. We can chat about that later. I don't want to spend that much time here. We have only 20 minutes, and I'm going to be talking a little bit of my adventures working with Linux and, yeah, like integrating embedded devices into client products. This will be more focused on the travel, on how did I manage to get into deploying these kind of systems, and also more into the things that I thought there were like a good way to start with, but then realized they were not. And, and yeah, let's move on. First, I really like this guy, Chris Simmons. I don't know if you know him. He has done a lot of documentation and a lot of books over embedded Linux devices and embedded Linux development. And his abstraction of embedded is really interesting for me. And this is like really the core of what I'm trying to deal with here with this presentation is that embedded is just a computer. Just a computer that is running in some place that you don't think as a computer. So basically, if you see something that, I mean, maybe I'm getting a little bit to the edge in this part, but maybe it's worth to acknowledge that embedded is just computing, right? So yeah, that's the main point of this. And where did I started looking at Linux integrations? In 2018, we were a really small company. We had like 3 people working. Like 2 people of those 3 were the co-founders, so yeah, we were like only 3. And one client asked us for doing an Ethernet switch with some specific MTU packages and also one specific form factor in the mechanic side, because the switch was needed for integrating some cameras, right? So what I was looking for was available in this chip, Kia Z98 and 97, and that switch processor was able to do what we needed, but it needed to be configured by SPI. And I said, like, okay, I know SPI, I know a little bit of microcontrollers with the PIC 16, and let's do just one program or look for the library to integrate this switch. And then I realized that in their webpage, Microchip actually put only the Linux file systems and not for the drivers, and not any library compatible with C or for PIC, PIC microcontrollers or any 8-bit microcontrollers, right? So I said, look, okay, I can integrate a Linux system, but I knew these things for that time. So I knew how to use basic Ubuntu, but not much, and I didn't know anything about the shell. I did know how to use a Raspberry Pi in a really easy way, in a really like with Raspbian and that kind of stuff. I had some theory from my degree of what was a kernel, but I actually never touched anything about that. And I knew about basic programming in C, and I quote that because then I realized I didn't know these things. I didn't know how to modify a kernel. I didn't know what exactly was a driver, and I didn't know the exact difference between different GNU Linux distributions. More like far from the hate, like what was the real difference between one management, or if you what could you do if you do not have any package management, right? And I did not know how to program in C. So basically, even though I thought I knew basic programming, I realized I didn't know. And there's a lot of things that I didn't know that time. And what happened, I went to basic C programming. I read all the SPI registers, modify them, and that worked. My switch was working. The device was able to control the PIC device was able to control the switch device, and then we were able to transmit at the speeds that we needed, which was 1 gigabit, and also with the MTU, which was, I don't remember, but it was one specific number that the camera needed. And yeah, that worked, but for me it was like, okay, that was a point where I realized that I didn't know much of Linux embedded, and I wanted to learn more of it. And yeah, that planted a seed. And the same client later in 2019 asked us like, okay, can you integrate now cameras, different cameras than the ones that comes with Raspberry Pi, like ArduCam or any OB from Omnivision or any IMMX from Sony or whatever sensor? And I said, okay, but I think I'm able to. There's a lot of documentation online. Let's try it. So the client specifically asks for a system that that needs to have two different cameras. That the supplier of the cameras has already the drivers compiled, and they offer you the binary, so you can just integrate to your kernel. And they offer you some instructions on how to change something called DTS for changing the control of the general purpose input-output, right? But the Raspberry Pi 3 or 2 that we had in hand by that time only had one MIPI port, right? So we ran into a problem. What was the problem? The form factor was too big. The SD card for something that is on field is not reliable. I don't know if you have worked with the Raspberry Pi, but it's really common, or it was really common right now. I think it's more stable. I'm not totally sure. I stopped using SD for a long time. But from what I remember on that time, SD were like completely pain. Like you were you were testing things, you were rebooting your system, and poop, kernel panic because something went wrong, because some service didn't go down in a good way, or a lot of stuff, or maybe just a shutdown of the power, and then your Raspberry Pi kills your SD because it was reading something, right? And last but not least, the Raspberry Pi 2 or 3 didn't support any more than one camera, and we needed to have two cameras. And then we were looking for different options, and we found the system on a module, which is a solution that is really known, I think, by the community, but it's worth to talk a little bit of it. Usually, the system on a module allows you to integrate one CPU, one RAM, one eMMC, and one PMIC, which is power management IC, and everything is packed down in a easy to solder, well, easy to integrate module in a PCB. So you don't need to run into this big layout for VGA kind of chips. You don't need to manage all the different voltages. You don't need to manage all the differential pairs for DDR4, DDR3 for RAM, or the MMC layout, right? And when we found this system on a module, the device, the system on a module that we found was the compute module 2, if I'm not wrong. Um, and it had already exposed the two MIPI CSI ports that we needed. And basically, it was the Raspberry Pi, but in a smaller package. So that led us to have the same integration as we would have in a full Raspberry Pi, and with all the support of the community and all the support from Raspberry Pi and the documentation. So we were like really comfortable going this way. Talking a little bit about the system on the modules, you will find right now a lot of different options, flavors, and each one has different approaches to the hardware and different approaches to the support and different approaches to the capabilities of the processor, right? Right here we can see some of Arduino, like X8. From Barry's side, we have MX6, if I'm not wrong, that one. We have some of Renesas, we have some of Broadcom with Raspberry Pi, STM32, which is also a processor, Cortex-A. So basically, you can integrate these big computers into your project in a really easy way, because you have a big footprint, you have a easy to solder connector. Well, easy to solder connector is relative because, for example, the Portenta X8 has these high density pins that are really hard to solder in hand, but if you send to manufacture to ULC PCB, it is really easy and it's not that expensive as it would be to integrate the one UPGA, right? So basically, this will allow you to integrate system on modules in a good way. And why did we kept in that part with Raspberry Pi? Because of the support. The support is the most important part in any Linux system when you start working with different vendors. This is really, really important, and that's why it's only there, like support, because if you're all by yourself out there working with a system that you didn't design from scratch, you won't know all the details on the schematic, or even if you have the schematic, you won't know all the details on the manufacturing, right? So we will see some examples of that. Long short story, we went with Raspberry Pi Compute Module 3, we bought some development boards, and we started working in the development boards. The integration was kind of easy. We create one specific hardware, one motherboard to bring the compute module to work. That won't be discussed because that gives a lot of topics to talk about. We integrate two cameras with different drivers. Each camera was a different camera, and each camera had a different driver to integrate with. So basically, we had to integrate two different drivers. We had to modify the GPIOs to turn off the camera and also to turn on some flashlights that the camera had inside, and assign one I2C for each camera because they were like having, even though the I2C in the cameras is only for sending commands, for us was better to split the two different I2Cs, one for each camera, so we would not have any collision while configuring anything on the fly while working. And one question remained: do I need to change the kernel? And the answer to that was no. We have one specific device resource file that gives you the ability to configure your same kernel in a different way with different hardware. So basically, with only one kernel, you can integrate a bunch of different drivers and bunch of different peripherals in a different way and configure them on the boot. Basically, this is a text file that you can read into any text editor. It needs to be compiled. So there's one device tree compiler that you can download and compile in the same Raspberry Pi or in your computer. Once compiled, you put the binary file right in some specific location of the /boot, and the bootloader will look for the device tree and load it to the kernel, so the kernel can configure all the peripherals. This is really important because the device tree source basically explains the drivers, the kernel, what drivers the kernel needs to find and how to configure them. Uh, you can use device tree source, and also there's another thing called overlays, which is an extension of the device tree source, and you can mount those overlays to extend the functionality of your device tree source. It is suggested by Raspberry Pi, in this case, to use overlays, because if you start moving the device tree source and you are not completely sure what you're doing, is pretty you can make the system fail, right? So basically, using overlays will keep all the other configurations untouched, and with the overlays, you can add some functionality, so or change on the fly the functionalities. One important part of overlays, even though they are really secure, not all the bootloaders support overlays, so that's a thing. And how can we see this? For example, this is a screenshot from Linux, from Raspberry Pi, the Linux repository that they have. And you can see how we have Linux, Arch, ARM, boot, DTS, and overlays. But if we go for Bodyside, which is another system on a module manufacturer, you will find Linux, Arch, ARM, boot, DTS only. They don't have any overlay. And that's why don't they use overlays? Because their bootloader doesn't support it. And you don't want to mess with that, because if their bootloader is not supporting something, you would need to change the bootloader, but you don't have all the environment to change the bootloader, and then you face more trouble. So basically, what I'm trying to explain here is that even though there are some standards to make this safer, not every company uses and not every company keeps them updated. And you can see even in the main repository of Linux, you can see the DTS that specific folder has a different bunch of stuff, and those DTS are not compatible with the DTS from Raspberry Pi and the DTS of Bodyside. And that translates in a lot of work. So in order to avoid these parts, always keep the support like your main importance part. Uh, Things can easily go wrong, and you will need help. The thing is, how can you get the help, right? I I suggest you to check the support with the manufacturer always before buying any development board or any kind of processor. Check the driver compatibility, and well, vendors are really slow integrating quick fixes or solving issues. So basically, if you before you buy any SOM, check the support that it has. Check the issues, the forums, the, what people is telling about this SOM, right? So well, those are some early conclusions and some parts that I think that are really, really important. Because what's next, once we had all that part, we figured out that the integration of the two cameras with the CM3 module was not powerful enough. So we said, okay, there's some other SOMs that are more powerful, and basically we can integrate those with our device. So we tried. We tried with Bodyside, but they do not support any camera outside of the cameras that they already support. So if you want to integrate something, you're by on your own. And then Solid Run was able to integrate the drivers that we had, but their U-boot was not working. So we spent like 2 months trying to make the U-boot working, and nothing came up. And then they deliver a solution, but that time, the CM4 have already come to the market. So we compared the Solid Run with Compute Module 4, and we decided to go with Raspberry Pi again. So Raspberry Pi saved the project again, and we did just the same integration as before. We did not need to change anything else. And that project was finalized by that. The project was split it in two. So we had one CM3 and one CM4, and those were for different analysis of the images. But I can tell you that both of them have been on the field for several years already. Now, that client has already finished. We are doing just the manufacturing of it. So another client comes and says like, okay, let's do displays. We want to do one specific integration where where we want to integrate one flexible display. And I said, okay, I have never done that, but I think we can, and I checked the documentation. So what I saw was the display that they wanted to integrate was a MIPI DSI, which is a display serial interface, and MIPI CSI is the one used for the camera. So I said like, oh, okay, this should be smooth as the cameras. And I said, yeah, we can. And then the AMOLED uses an RM692299 for the display integration. And I said like, okay, let's Google this. And I saw a patch in Linux from 2019, and I said, yeah, we're able to integrate that because it's already in the kernel. And the client wanted to use VariSide because it supports Android, and the client wanted to use Android. So the automatic response for me was like, oh yeah, we can. This is something that we can do. The reality was that we were not prepared for it, or sort of. These were the challenges. I had these resources to make this work. I just had one data sheet that later, like 9 months later, I realized was a bad data sheet. So I had to talk with the Chinese people to see like what happened, why do we have a bad data sheet. I had the display screen, I had 2 adapter boards, a patch from 2019 in the kernel, one VariSide development kit, and one VariSide ticket system where I was putting all my questions, right? This is the patch. As you can see, it's 2019, November 14. And this was integrating the specific driver chip that I was using. And those are the boards that I had. I had the screen, I had the green board as an adapter, and the blue board as an other adapter. Basically, the blue board is one MIPI to HDMI, MIPI to the HDMI translator. But we wanted to talk with MIPI to the actual display. So, and in the green board, you can see some specific IC right there, which is a DC converter. For the AMOLED displays, you need to have some specific voltages for having the screen to be light up in like negative voltages and positive voltages. So this DC-DC is really specific, and the screen communicates with it. So it needed to be like this specific IC. So what I thought was, okay, this green board will work for me because it has all the DC-DC integration already. So I did one specific adapter board for the development kit, and this was how it ended working, right? So you have the screen, the green board, then the flex, the really big flex that we have in there, and then we have the MIPI board. So time to do code. This was like, oh yeah, let's integrate the device resource. Let's bring up this specific module from the kernel that already exists, and this will work. Well, spoiler alert, it didn't work. And well, didn't work. This is why it didn't work. I needed to put one specific environment for compiling Android. I just follow the specific guide from VariSide. They have a good documentation on that side. They said like Ubuntu 22 worked, but it never worked for me. I had to use Ubuntu 20. And then understand how the Linux kernel is integrated to Android. So they use this generic kernel image that you can retrieve different modules and different drivers from the Linux, the LTS Linux version that you are handling on the kernel. So basically, what I needed to do was in this specific file, adding the specific driver that I wanted to integrate in the GKI fragment. So the GKI can look for the driver and integrate into the compilation. And we had the DTS, the device resource. Basically, I added the device resource of the MIPI device that I wanted to integrate. Everything compiled, but not never work. And basically, never turned on the display, and the logs were showing that the DSI was not able to attach to the peripheral. I talked with the body side people like for several months, and they told me, okay, give me your specific part number of the system on a module. Turns out there were some resistors that I needed to remove to enable the MIPI port, and that was not able. That was not even in the data sheet or in the schematic. But I mean, that's why support is that important, right? So I said, okay, this is gonna be working now, and nope, it was failing to attach again. So we kept all this integration problem trying to keep it solved, but we never found what was the problem. But my curiosity was like, okay, they are not explaining me why it's not able to attach to the DSI peripheral. But I thought maybe this is a problem between the codes. So I decided to look for another code that was similar for the RM6791, and then I integrated to the kernel and then compile it and see another problem, not the attach problem, but display not found. So the commands were not answered. And then I start coding there my actual driver, and I did all the initialization of the driver. Before of this, I didn't know much of drivers or this integration, but now I see this part of drivers just as writing bare metal C programming. You can read the data sheet, you can integrate the driver, and then specify all the specific number and names for the device resource to match it. And basically, I just add some specific functions, as you can see in there. And as any bare metal, you just follow the datasheet. You had some utilities from Linux, so that's really helpful. Having the DSI library, having the sleep, the GPIO control was all that I needed to have. So I code all the, you can see that's the code that wake up the screen. And yep, that worked. And yeah. I'm running out of time, so basically the challenges are moving to another processor. The conclusions that I want to give, just a little bit, integrated Linux is not simple, but it's worth it. It is really stable when you manage to have it. Always check the support of the manufacturers. Double check the documentation is still being maintained and updated. And also working with people, or things like this could speed up the process. If I did all this on my own, but I think some ideas could come faster if there was more brains in it. And the most important conclusion, write your own drivers is not that complicated, but also you can create bad code that will kill your system. Breaking your system is not bad, while it's not in production or in field.